How will you implement this? So now you design controller, the adaptive controller as tau equal to y transpose theta dot theta hat plus kr, and y hat is a time variant signal that estimates the system parameters. And so you have to learn the dynamics is theta hat dot, and this is the is designed to be again times the regression matrix R, regression matrix Y and R, okay, the Churchill error signals. We call Y as a regression matrix. Regression. Okay. And this is filtered Churchill error. So you know the regression matrix, right? Which is a function of z trajectory and the Churchill error E dot and some measurable terms Q. So everything here is known. So you can implement this. For theta hat is a time variant signal. It follows this dynamics. Okay. So to obtain this, you need to integrate this. Okay, you need to integrate the adaptive law of theta hat. Okay. You're trying to learn or adapt to the true signal. Trying to use this rule to learn the true parameters, although it might not eventually converge to the true signal. Okay. So the way to obtain this, so in your controller you implement this and this. Everything is known, right? But here we need to do one more step, which is you need to integrate this from 0 to t. Okay, given any initial conditions. And this is user's choice. Okay, you can put whatever initial condition you want and integrate this. Okay, in the block diagram, this is system, right? It takes the input and generate the output, which is Q and Q dot. Okay, and here's the controller. Okay, it's trying to track some QD signal. Okay, and here's the feedback. Here's the controller. Here. So the way to generate this tau is compute these two terms. So R gain is the control gain you can select. R is the filter tracking error, which is you can do some filter tracking error here. Okay. Say R equal to E dot plus alpha E. Okay. So you can obtain E dot and E both from here, or QD dot, filter checking error. Tracking. Error. Okay. And in here, you have theta hat, which is time variant. So you need to you need to do this. Okay, one more block doing this. And this generates the updated theta hat. And that's required for the controller to implement. So the difference is, not only have feedback, you have feed-forward term, and feed-forward term is coming from adaptive, coming from time-varying signal, which is updated according to the adaptive law. Okay, adaptive law here. Okay, but for robust, you just do KR here, right? KR and plus K2R. It doesn't require theta hat. Okay, that's the difference. And the benefit of introducing these terms give you global asymptotically stable, which we're going to prove in the next few steps. So this is for control implementation. And here we say V is PD, but Vita is an SD. But you can use Barbara's lemma to show that R will eventually converge to 0. According to 6 and 1, we can show that both signal R and theta tilde are bounded, right? Because Vita is negative semi-definite, right? So V, the largest value of Vita is 0. That means that V cannot increase. The worst case is V is hold at constant, right? It only either decrease or hold at constant. It never increase. That means that both signal R and theta hat will be bounded. Now you can apply Barbara's lemma to show R converges to 0 as t equals to infinity. So next slide, we call it signal tracing. So it starts from these two signals, which are bounded. Okay, V is bounded, so both signals are bounded. And because tilde is bounded, and this defined as theta tilde equal to theta minus theta hat, and because it's a constant, if this is bounded, this will also be bounded. So theta hat is also bounded. Okay. So what does that mean? That means that no matter what initial condition you selected, the integration of this term will remain bounded. Because this guy, the guy you are integrate, have Y and R signal, right? And both are time variant. If you are integrate something that is always positive, eventually it will go to infinity. If you are integrate something that is time variant, Y and R, and it's hard to tell, you can use the above function, and do the signal tracing and give you that no matter how you integrate, this signal will remain bounded. If I just ask you, here I integrate some signal, right? From 0 to t goes to infinity. Okay, is it bounded? Because in the control, everything had to be bounded, right? We already show R is bounded. K is constant, so this term is bounded. Okay, and this term should be bounded. It's a function of error signal desired trajectories. Okay, so the questionable term is this term. Because if it's unbounded, control input will be unbounded. You cannot ask a system to generate infinite large control output, right? No real mechanical system or electronic system can do that. If you are controlling the motor, this is torque, right? You cannot generate an infinite large torque, right? So that means that all these signals have to be bounded. And this is the way we show that it's bounded. Okay, it's hard to tell from here that if theta hat will be bounded, because you're doing integration here, it's hard to tell, right? Because you are integrating some time variant signals. But using the above function approach, okay, we say based on 1 and 6, both signals will be bounded, right? And because this is theta tilde is bounded, and from the definition of theta tilde, this is constant, this is bounded. It has to be bounded, right? It now is proven to be bounded. So we don't need to worry about the control output. We show it's bounded. What else? Because R is bounded, based on the filter tracking error properties, both signals will be bounded. So if this is bounded, both will be bounded. As here, R is bounded, so both will be bounded. This guy means it is uniformly continuous. Right. Okay. And now you can check. So this is bounded, bounded, bounded. And this term, you need to check out this term. So this term is a function of Q E dot Q D double dot. Why? Because based on the definition of regression matrix, it has QD double dot, right? You have E dot and Q. So is it bounded? You need to, if you want to check whether it is bounded or not, you need to check these three signals. Q and E dot is bounded here, based on here, so it's bounded. Okay, it is bounded. QD is bounded because it's user choice. Okay. QD is acceleration of desired trajectory. You always desire trajectory that 2 times derivative will be bounded. Okay, so both will be bounded, and this for sure will be bounded because from the definition E equal to QD minus Q, and from here, right, it's bounded, and this is user's choice, which will be designed to be bounded. So this guy have to be bounded. So Y will be bounded, and therefore tau will be bounded, and that's important. Okay. So do you see how powerful it is? The Lyapunov function is. Originally the problem was I give you open loop dynamics, right? MQ double dot plus blah 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 equal to torque, right? And you design torque as this. And remember, dynamics is nonlinear. You don't know the solution. You design adaptive control. Okay. At that time, you have no idea whether it's bounded or not. It's required to be bounded in practice. So you have no idea, right? The next thing you need to do is to design the Lyapunov function, take the time derivative, do the stability analysis, and eventually give you all the signal tracings. And you can check whether the signal you put in your control is bounded or not. Everything is on a paper and a pen. I give you a dynamics, a ODE, second order or first order, and you can tell someone just by hand, by a paper, say the controller, the design of this will be bounded. Okay, and this is the way you show him, convince him that it's bounded. So this is how powerful the Lyapunov function is. And next, we haven't done yet. We want to show that R will be 0 as t go to infinity. Okay, so we want to use Barbara's lemma. So using this closed loop dynamics equal to that, and because every signal here is bounded, and M is a constant, so R dot had to be bounded. For R dot to be bounded, R is uniformly continuous. And that's important to show that it's to use the Barbara's lemma. So next step, and remember the Barbara's lemma, the lemma says a signal had to be infinitely continuous and it had to be L2 function. And then you can show that you will converge to 0 as t equal to infinity. You need to also find R's L2 function. Okay. Remember, we show that V dot is NSD in the previous slides. And if you take the integration, you integrate both sides. You got Vt minus V initial condition equal to this guy. Okay, and this is bounded. this is bounded, right? Because V cannot increase, it only decrease. So given some initial condition, this guy will always between this value and 0, right? Because P is PD and the largest value is V0. So this have to be bounded. Both will be bounded. So this means it will be bounded. And that says R is R2, L is a L2 signal, R is a R2 signal. R is uniform continuous and R is L2. We can show that R converges to 0 as t going to infinity. So we show control is bounded, R converges to 0 as t go to infinity. Some of you might not believe this, and one of the controllers is adaptive control. Another one is robust control. You need to implement this controller and show whether the control input is bounded and R converges to 0. Summary, adaptive control, the control structure is this. And you need to estimate the theta hat based on the adaptive law. And the result will be globally assumed. For robust control, VR is the robust term and KR is the feedback term. VR is designed same as some constant times R, and the objective is to deal with the uncertainties or the disturbances, and you will get UUB. By increasing the gains, the UUB ball, the steady state error can be decreased. Okay. 所以这样 V 大会变什么 ？ND 吗？决定。你的 V 是什么？这样就好麻烦，还没结束。再来。Signal tracing 你要做啊，你等一下，你私底下来做。So yeah, that's right. Here is how we will do it. Give you an example. Everything is the same other than you just eliminate this. Eliminate this. Okay, then it's same as this. Everything below step 3 are the same because the difference in dynamics has been narrowed down, have been condensed in Y transpose theta, right? And everything remains the same as previous slides, okay? So in your controller is also different. The difference is Y transpose and theta, as well as theta hat. So you need to look into detail how step 3 to step 8 are doing. What's the strategies? If you have unknowns, how you can cancel the unknowns, or how you deal with unknowns, and how you apply adaptive law to cancel out some terms here. Theta, and because you are in your tau, you have Y theta hat that can be combined with Y theta, and that create Y transpose theta tilde. Okay. And this Y transpose tilde can be cancelled by this adaptive law. So basically, if you change the dynamics, you need to cook the V dot, and somehow it becomes this form, okay, which is the universal form for adaptive control. Because in this case, theta is a scalar, so you don't need to write. You can reduce to a scalar form, which is theta tilde squared and 1 over gamma, okay, because gamma inverse is equal to 1 over gamma in the scalar case.